So we are going to start today with this chapter called the D and F block elements. The first point is, what are the learning objective of this chapter? After studying this unit, you will be able to explain what are basically D block element, what are F block elements, where exactly they are being located in the periodic table. Number one. Number two is, what is the electronic configuration of transition element? What are inner transition element? Of course, transition element are D block elements, and inner transition elements are nothing but they are basically the F block elements. Then we have what what is the relative stability of vary of oxidation state in terms of their electrode potential value. Then we will study about the general characteristics of D and F block element on the basis of their horizontal group. And of course, beta, last we will be taking up F block element, where we will do a little bit of comparative study of lanthanoids along with the actinoids. Although actinoids as such is not in the syllabus, but still we will take up the electronic configuration, oxidation state, and chemical behavior for it. Now let me start that what are basically D block elements are. Now, if you see the periodic table, this is the periodic table, where on the extreme left hand side we have the S block element, on the extreme right we have the P block element, and this S block element and P block element are collectively or normally called as normal or representative elements. And in the centermost we have the D block element, which are basically called as transition element. I was saying other day also the same thing. Transition mean when something has an intermediate property. Transition means when you are going from one phase to another phase, the intermediate state is nothing but it is exactly called as transition status. Here also, transition basically means is nothing but it is what? Transition basically means is what? The intermediate oxidation state or intermediate state. That's basically called as transition state is. Now, let's start what is basically a D block element is. If you look at this diagram, where we have actually seen this is the outermost shell, which is actually represented by NS. This is the outermost shell. One inner to the outermost is nothing but it is actually called N-1D, penultimate shell. One inner to the outermost. So we used to say that the elements in which the last electron enter into the D subshell, of course, D subshell, which is of course N-1D, as I said, penultimate shell of their lowest energy level, they are basically called as D block elements are. When you talk about the general electronic configuration of D block element, it is N-1D 1 to 10, NS 1 to 2, where the value of N is from 4 to 7, and of course N is nothing but it is called as the principal quantum number, right? Or also sometimes called as the period of the periodic table. It is called as the period of the periodic table. So the elements in which the last electron enter into the D subshell of their lowest energy level, they are basically called as transition element R. The point here is this NS and N-1D, the NS and N-1D, both have a compatible energy or comparable energy. Since both of them have a compatible or compatible energy, that's why both of them can take part in chemical combination. So first definition is that the D block elements are generally those in which the last electron enter into the D subshell or the lowest energy level. In the case of representative elements, the added electron, if I am going to compare the D block element with the normal or representative elements, in the representative elements or in S and P block element, only the outermost shell can take part in chemical combination. But when I am talking about D block element, not only the outermost shell, but one inner to the outermost shell can also take part in chemical combination. That's why we say that they are basically called as what D block elements are. And as I said, they are actually intermediate in between S and P block, or they are sandwiched between S and P block. Their properties are always in between S and P block. That's the point which is here. Now, Let us start. When I say the general electronic configuration of D block element is n minus 1 D1 to 10 ns1 to 2, where as I said n is from 4 to 7. The point is, if here we have n is equal to 4, suppose in the periodic table this is n is equal to 4, that means this is 4. As per this, if n minus 1 D1 to 10, as I said, as per the electronic configuration, if n minus 1 D1 to 10, if I'll take up this concept, if n is 4, that means here it is 3D. This 3D is nothing but it is called as the first transition series. This is called the first transition series. And here we will fill up the elements starting from, this is where we are going to fill the 3D transition series or the first transition series, where as I said n will be 4. We will fill up Z21 to 30, that is scandium to zinc, in which we are going to fill the 3D subshell is being filled, where as I said jahan n ki value jo hogi that is 4. In the same way, if I'll take up n is equal to 5, agar main n is equal to 5 leta hu, so in that case, as per this will be 4D, which should be called as n is equal to 5 ke liye. This is 4D. This is called the second transition series. Second transition series. Of course, the second transition series starts from yttrium, atomic number 39. So it starts from 39 and ends up at 48, which is nothing but it is cadmium, where 4D subshell is being filled, and it is a part of the fifth period. Now let's go to, if n is 6, beta, when n is 6, you will find that if n is 6, of course you will try to fill the 5D orbital. But the point here is, if I'll try to fill the 5D orbital, and if you see the Aufbau principle, according to the Aufbau principle, 4F should be filled before the 5D subshell. 4F should be filled before the 5D subshell. So that's why before this atomic number 57, or atomic number 57 is lanthanum, where of course the 5D orbital has been filled. But since this is the first element of the 4F series, which is of course the 4F series, which is down here, starting from 58 is here, and it goes till 71, which is lutetium, then 72 hafnium is again this. It goes till atomic number 80, which is mercury. This series is nothing but it is actually called as the 4F or inner transition series. This is called inner transition series because of course it is coming from the, or we can call it as the first inner transition series, or also called as lanthanoid series. Why? Because the first element is nothing but it is lanthanoid. When n is 7, if n is 7, of course we are going to fill here the 6D orbital. 6D orbital here. So if the 6D orbital is being filled, in that case the first element is nothing but it is actinide. But the point again, 5F has a higher, or 5F should be given a priority before that of the what, your 6D. So that's why here again the 5F series will be filled, which is nothing but the first element, as I said, is nothing but it is actinoid 89. 90 is thorium, it goes till 103, which is lawrencium, and then 104 is rutherfordium. So here 112, it will be the last element, 112 will be filled over here. So we have to just take up an idea that there are 3D, 4D, 5D and 6D series that are basically being present in the D block elements are. But right now the most important point that we are going to take up is that what are basically transition element are. There are 2 points that we have to consider right now. Number one, Transition elements are basically those which have partially filled d orbital. I repeat, transition elements are generally those which have partially filled or incompletely filled d orbitals. I repeat, or any element which has partially filled d orbital or incompletely filled d orbital, they are nothing but they are basically called as transition element are. So I have written the definition also. They have partially filled or incompletely filled d orbital in their neutral, elementary, or in their common ions, or they must have. This is the first point. This is the first point, that transition element must have partially filled or incompletely filled d orbital. I have seen that there are few books which write they have vacant d orbital. Please don't write vacant d orbital. It is partially filled d orbital or incompletely filled d orbital. The condition number second is, if they do not have a partially filled d orbital, you can check whether they have a variable oxidation state or not. This is the second condition. So transition elements are basically those which have partially filled or incompletely filled d orbital configuration, number one. Number two, they must have variable or multiple oxidation states. Now let's take up the questions on the basis of this. Beta, there was a question which was asked in CBSE 2015, and it was, what are transition element? So we have already done. Transition elements are generally those in which there are two conditions that are being satisfied. Number one, they must have partially filled d orbital or incompletely filled d orbital. Number two, they must have variable oxidation state. Now the point is, what are the two characteristics of transition elements? The two characteristics of transition element include, they are very good catalyst, they form alloys, they have variable oxidation state, they have E naught values, most probably the positive values or negative values, right? So these are the characteristics of transition element are. Now let us take up the most important point right now, and that is, when I was writing the electronic configuration yesterday, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. This is the 3D series where atomic number is 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. There are two exceptions in 3D series. One is, of course, chromium, which has a half filled d orbital configuration. And in the same way, if I am talking about your copper, which is atomic number 29, where there is a completely filled d orbital configuration. D orbital configuration. Now let us take up, I'll write here first argon 18, scandium is 3d1 4s2, titanium is 3d2 4s2, vanadium is 3d3 4s2, chromium with an exception 3d5 and 4s1 because it is half filled. 3d5 has a half filled d orbital configuration. When I go to chromium, manganese has 3d5 and 4s2, iron has 3d6 4s2, cobalt has 3d7 4s2, and then nickel has 3d8 4s2. Then we have copper, which has a fully filled electronic configuration of 3d10 and 4s1. In the same way, zinc 3d10 and 4s2. This has a completely filled d orbital configuration that we have already done. Now when I was taking up this, the definition, one of the child said, sir, in 3D series, zinc has 3d10 configuration. In the 4D series, cadmium has 4d10 configuration. And in 5D series, suppose mercury has 5d10 configuration. So zinc, cadmium, and mercury should not be considered as transition element. So this is the first question that we are going to take up. Why zinc, cadmium, and mercury are not considered as transition element, although they are being placed with the transition element? Answer is very simple. Zinc, cadmium, and mercury, zinc 3d10, cadmium 4d10, and mercury have fully filled d orbital configuration in their elemental or in their commonly occurring oxidation state, so they should not be regarded as transition elements. In the same way, if I'll take up example 8.1, on what ground can you say scandium is a transition element but zinc is not? Answer is very simple, because scandium has 3d1, which is commonly has half which has incompletely filled or partially filled d orbital configuration in the ground state, that side should be regarded as transition element, while zinc 3d10 as a fully filled electronic configuration should not be considered as a transition element. Now there is another point that we have to take up right now. There are three elements. Just before the zinc we have copper, just before the cadmium we have silver, just before the mercury we have gold. Now all three are nothing but they are collectively called as coinage metals. I repeat, all three are collectively called as coinage metals. Now when I'm talking about copper, again it has a configuration of 3d10. When I'm talking about silver, it has 4d10. But if I'm talking about gold, it also has 5d10 configuration. Now the question arises, then why do we call copper, silver and gold as transition element? The answer is because if we consider copper, although they do not satisfy the first part, that or first condition, that they do not have partially filled or they do not have partially filled or incompletely filled d orbital configuration, but the point number second is being satisfied, that they have variable oxidation state. For example, copper is copper 1 and copper 2, variable oxidation state. Silver also has 1 and 2, again variable oxidation state. Gold again has copper 1 and copper 2. That means they all have variable oxidation state. So that's why they are considered as what? Transition element. So there is an in-text question, and that question is, silver atom has completely filled d orbital configuration in the ground state. Why it is considered as a transition element? Because it has a tendency to show or it display variable oxidation state. That's why it is considered as a transition element is. Now we will take up example 8.8. Question is, what are the characteristics of transition element and why are they called transition element? Which of the D block element may not be regarded as transition element? See, I have already taken up the transition element are basically those in which not only the outermost, one inner to the outermost, which is called penultimate shell, take part in the chemical combination. Characteristic, of course, is this only, because Ns and N-1D have a compatible energy. Why they are called transition element? I told you, because their properties are intermediate in between the S and the P block, or they are because they are sandwiched between both of them. That's why. Now, which of the D block element may not be regarded as transition element? You know, zinc, cadmium, and mercury should not be regarded as transition element, although they have been placed with the transition element. Then we have exercise question 8.9. In what way is the electronic configuration of transition element differ from that of non-transition element? But I told you very clearly, when I'm talking about normal or representative element, only the outermost shell can take part in the chemical configuration. So the general electronic configuration for S block element is NS 1 to 2. For P block, it is NS2 NP 1 to 6. But when I'm talking about D block element, right, it is N minus 1 D 1 to 10 NS 1 to 2. I have seen a book where it was written that the transition element should be given a definition or should be written as an electronic configuration of this N minus 1 D 1 to 9 NS 1 to 2, because if I am writing N minus 1 D 10, then in that case 1 or 2, in that case it will be zinc, cadmium or mercury, which are not actually considered as transition element. That's why that book has actually mentioned this. The configuration should be N minus 1 D 1 to 9 NS 1 to 2. This is what they have written. So I hope now this part is clear. We will now take up the next topic. We have done all of them. Now let's go to the physical properties. Let's go to the physical properties and electronic configuration of the transition element. When I'm talking about the physical properties and of course the electronic configuration of transition element, I have already taken up the electronic configuration, so I'm not going to discuss the electronic configuration right now. I am directly going to the physical property, and of course that's the atomic radii. So I'm going to the atomic radii, the first physical property that we are going to discuss right now. Now, if this is the periodic table, and as I said, this is S block, This is your P block and this is your D block, of course, transition element. We have already done that whenever we move from left to right, the atomic or ionic radii, atomic and ionic radii decreases. The reason why does the atomic and the ionic radii decreases whenever we move from left to right in the periodic table is because the nuclear charge, or there is another term which is used, it's called effective nuclear charge. I repeat, whenever we move from left to right, from here to here, there is a term which is increasing. It is called effective nuclear charge. Effective nuclear charge. I repeat, effective nuclear charge. Since that is increasing, it will always try that the atomic and ionic radii will decrease. So from this, what do we conclude? As I have written, we conclude that S block element has the highest atomic radii, then D block has the intermediate, and P block has the least atomic radii when you try to move from left to right in the periodic table. So that's why the statement that I have written is the atomic radii of transition element are smaller than S block, but it is larger than that of the P block elements. This is what I have written. So we will now take up the trend which is there in the 3D series, which is very, very important. So I'm going to take up that what is the trend in 3D series. Beta, whenever we are talking about the 3D series, there are three trends that are being taken care of. This is 3D series: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. The first trend is that whenever you try to move from left to right, the first trend is whenever you try to move from left to right, beta, the atomic radii till the midway decreases. This is the first trend of the atomic radii in 3D transition series. The second is from iron to copper, you will find that the atomic radii is almost constant, And beta, the last one is in the zinc, the atomic radii increases again. So there are three trends. Trend number one, till the midway atomic radii decreases. After the midway atomic radii become constant, and finally at zinc atomic radii increases. So now we will take up the concept that why exactly it happened. If you see, I have written here the atomic radii of transition element are smaller than that of S and larger than that of the P block element in a period. The first trend is in a transition series, as the atomic number increases, the atomic radii first decreases till the middle, become almost constant, and then increases towards the end of the period. Of course, that is not regular. That means it is not regular. Now, the point is why. This I have to discuss now. But if I am not wrong, there is one thing which I have discussed just now. If I'll try to move from left to right, I repeat, whenever I'll try to move from left to right in 3D series, there is one thing which is actually increasing from left to right, and जिसका मेन मोटिव यही है कि किसी तरह से भी एटॉमिक रेडियाई को डिक्रीज किया जाए. I repeat, there is one thing which is actually increases with increase in atomic number, and that is nothing but it is exactly called as nuclear charge. Nuclear charge, or there is another term which is called effective nuclear charge. इसका मेन मोटिव एक ही होता है कि किसी तरीके से भी साइज को डिक्रीज किया जाए, किसी भी तरीके से साइज को डिक्रीज किया जाए. So the same thing is here. When you are trying to move from left to right, the effective nuclear charge is actually decreasing, or sorry, increasing from left to right. But now the point is, सर यहां तक तो समझ में आ गया कि अगर हम लेफ्ट टू राइट मूव कर रहे हैं तो यहां तक न्यूक्लियर चार्ज जो है वो काम कर रहा है और इस वजह से एटॉमिक रेडियाई डिक्रीज करता जा रहा है. बट द पॉइंट इज why does it become constant from iron to copper? The point here is because there is another point which came into the picture, and that actually is after the midway. There is a point which is called shielding effect, screening effect, also called as repulsive factor, also called as repulsive factor, which came into the picture over here. Now the question is, sir, how does it is playing a role? The point right now that we have to understand, जो हमें समझना है ना, वो ये है, ये न्यूक्लियस है मान लीजिए, and suppose beta this is your 3D. 3D is inside, and as I always used to say, if I have to draw 3D, I repeat, if I have to draw 3D, I always used to draw it by using dotted lines. Why? Because as I said just now, 3D has a poor shielding effect. If 3D has a poor shielding effect, that means it can't shield the nucleus. And if this dotted line is showing, what? 3D series, and this is my 4s. The point right now is, if there are two electrons, the electrons are entering over here. First electron, second electron, third electron, fourth electron, fifth electron. क्वेश्चन जो आपका आना चाहिए वो ये है, सर ये तो समझ में आ गया, स्टार्टिंग में एटॉमिक रेडियाई डिक्रीज कर रहा है. सर वो इसलिए डिक्रीज कर रहा था क्योंकि न्यूक्लियर चार्ज या इफेक्टिव न्यूक्लियर चार्ज जो है वो बढ़ रहा था. बट सर मिडवे के बाद क्या हुआ? सर मिडवे के बाद यह हुआ कि इसे काउंटर बैलेंस करने के लिए एक इफेक्ट आ गया यहां मार्केट में, जिसका नाम है शील्डिंग इफेक्ट, स्क्रीनिंग इफेक्ट और रिपल्सिव फैक्टर, which will try to counterbalance it. And since it will try to counterbalance, what will happen? The nuclear charge is increasing. न्यूक्लियर चार्ज तो बढ़ता जा रहा है और इलेक्ट्रॉन यहां ऐड जरूर हो रहा है. क्योंकि ये इसे शील्ड नहीं कर पा रहा, तो इसका मतलब ये इसे इलेक्ट्रॉन को बहुत स्ट्रांगली अपनी तरफ न्यूक्लियस पुल करेगा, तो एटॉमिक रेडियाई छोटा हो जाएगा. बट द क्वेश्चन इज, सर ये 5 के बाद ही क्यों आया? सर व्हाई ओनली आफ्टर दिस? सर लेट अस अंडरस्टैंड द पॉइंट. बेटा डी ऑर्बिटल के पास अगर हम देखें, डी सबशेल के पास 5 ऑर्बिटल होते हैं, 1 2 3 4 5. नाउ when the first electron is added, I said there is no shielding or screening effect, क्योंकि shielding और screening को repulsive factor भी कहा जाता है. जब सेकेंड इलेक्ट्रॉन ऐड होगा तब भी ऐसा कुछ नहीं होने वाला, there is no shielding or screening effect. When the third electron is added, again there is no shielding or screening effect. When the fourth electron is added, again there is no shielding or screening effect. When the fifth electron is added, again there is no shielding and screening effect, because there is no repulsion over here. Electrons are being easily added. But now if this sixth electron will try to come and will try to occupy any of this degenerated orbital, all these 5 will try to repel this. और जैसे ही इसे repel करेंगे तो screening effect, shielding effect, screening effect या repulsive factor will try to come into the picture, और वो counter balance करना start कर देगा. किसको balance करना start करेगा? न्यूक्लियर चार्ज को. इसी वजह से जैसे जैसे ये 6th इलेक्ट्रॉन गया, काउंटर बैलेंस होना स्टार्ट हो गया. 7th इलेक्ट्रॉन काउंटर बैलेंस, 8th इलेक्ट्रॉन काउंटर बैलेंस, टिल द टाइम यू रीच टू दिस कॉपर, ये पूरी तरह से काउंटर बैलेंस कर देता है. और जैसे ये पूरी तरह से काउंटर बैलेंस कर देगा, अगर आप इलेक्ट्रॉन, लास्ट इलेक्ट्रॉन यहां पर एंटर करेंगे तो क्या होगा? इतनी ज्यादा इंटर इलेक्ट्रॉनिक रिपल्शन होगी कि एटॉमिक रेडियाई फिर से इंक्रीज हो जाएगा, बिकॉज द electron cloud will try to expand. Now what I was trying to explain is, in the beginning of the series, the increased nuclear charge predominates the weaker shielding effect, and the atomic radii will decrease, because there is no role of shielding or screening effect till manganese or till the midway. Later on, the increased shielding effect and the increased repulsive factor between the electron will tend to compensate. I said after the midway what will happen? Now the shielding, screening और repulsive factor will counterbalance, और जैसे ही वो counterbalance करना start करेगा, atomic radii will become constant. And जैसे ही हम कॉपर पे पहुंचे, जो शील्डिंग और स्क्रीनिंग इफेक्ट था उसने पूरी तरह से न्यूक्लियर चार्ज को क्या किया? काउंटर बैलेंस कर दिया. और इसीलिए जैसे ही मैंने लास्ट में जिंक पे इलेक्ट्रॉन ऐड किया, इतनी ज्यादा इंटर इलेक्ट्रॉनिक रिपल्शन होगी कि इस इलेक्ट्रॉन क्लाउड का साइज जो हो जाएगा, इस 3D इलेक्ट्रॉन क्लाउड का साइज एकदम इंक्रीज हो जाएगा, एंड दैट्स व्हाई द एटॉमिक रेडियाई इंक्रीजेस. At the end, the inter-electronic repulsion between the orbital exceed the attractive forces. That is what I said. Nuclear charge से बढ़ जाएगा to increase the nuclear charge, so the electron cloud will expand. And that's why, as I said, so due to the increased nuclear charge, so the electron cloud will expand, and that's why the atomic or ionic radii will increase.